To better understand quantum computing and its applications, it is necessary to first differentiate it from what we consider to be a computer in today's world. These computers are known as binary computers. Quantum computers have been regarded by many as the computers of the future. These computers are known as binary computers. They operate on a system of ones and zeros, where 1 is on, 0 is off, to form what we call binary string. Quantum computers, on the other hand, use qubits that can exist in a superposition of states at any given time, essentially being a 0 or a 1, or some combination of that until they're measured. It is only at the time that the measurement is taken that the value is determined to either be a 0 or a 1. In conventional binary-based computers, we use logic gates to perform mathematical operations, whereas in quantum computing we use what is known as a quantum gate and the properties of superposition and entanglement to perform these similar operations.
In quantum mechanics, there were many key contributors who helped expand the field. In 1981, scientist Richard Feynman proposed the idea of quantum computing to solve difficult quantum mechanic problems that couldn't be solved before. In 1985, David Deutsch then proposed using a Turing machine invented by Alan Turing in order to simulate quantum computation. This computer could simulate algorithm logic. Together, in 1992, Richard Droza and Deutsch had proven quantum computing was faster than any classical computation methods used in the past. Just 2 years later, Peter Shor came up with an algorithm that could not only factorize large integers, but could do it efficiently. These scientists had created the foundation to help groups such as HP, Toshiba, D-Wave, and MagiQ continue to research and expand quantum computing.
A problem we have consistently mentioned in class is the many difficulties and impossibilities of solving more complicated systems for atoms with more electrons than something like a hydrogen atom. By utilizing states that do not exist in the classical world, exponentially increasing computation, teleporting quantum states, and many other things that are currently impossible are made possible. This would mean, for example, that instead of having to estimate a wave function using the variational theory and perturbation, we would be able to solve for a many-body system exactly using quantum computing. There are several real-life tasks for which quantum computing will be useful. One mentioned most often is that they will be able to read secret messages communicated over the internet using cryptographic protocols based on the hardness of number-theoretic problems like factoring and discrete logarithm. Additionally, quantum computing would allow us to model quantum systems without actually creating them. For example, we would be able to model the behavior of atoms and particles at unusual conditions, such as very high energies that can only be created in the Large Hadron Collider. We could also model chemical reactions, because interactions among atoms in a chemical reaction is a quantum process. Another use of quantum computers is being able to search through extremely large amounts of data, allowing us to be able to perform tasks like search through numbers in a phone book or find two equal numbers in a large amount of data with ease. Quantum computing would allow us to run simulations while actually producing results that binary computing could never dream of running in a number of different fields such as biology, engineering, chemistry, defense, energy, finance, among other things.
While all these applications may seem to be a wonderful thing, there is another issue other than just producing a working quantum computer, which is the programming of such a computer. Simulations and models cannot simply be copied from a conventional binary computer to a quantum computer and be expected to run. We need to develop a new way to program and interface with these computers to be able to perform any sort of tasks at a level greater than that of binary computers that we use today. Before we can reliably create and program a quantum computer, we must stick with our binary computers, even though they are quickly reaching their physical limitations for their speed and size.